Oh, sorry, 2 seconds. I completely forgot I moved my camera. Sorry, that was nowhere near as elegant as I thought it would be. Sorry, 2 seconds. Although I'm sure you'd probably much rather just look at the crashing waves than my face, but nonetheless, my face you're going to have. So welcome back. I hope you managed to have a good break over lunch. So this morning, obviously, we talked about discrete event simulation, and you had a chance to sort of design some discrete event simulations, and really the main purpose of that was to get you used to the concepts of what a discrete event simulation looks like. And I think you all did really well at that, to get your heads around what these things look like. Now this afternoon we're going to see how we build these things in Python, and we're going to use a package called SimPy in order to do that. And SimPy is a really fantastic free and open source package that allows us to take shortcuts when we're building discrete event simulations. As I mentioned a few times, it is a bit odd. I will say that there's quite a lot of information coming at you this afternoon, and when you first look at it, you might be a bit overwhelmed. Don't panic. Part of the reason you've got such a long exercise again this afternoon is A, because you've got quite you have to develop a model, but B, it's to give you a chance to also look back and understand how these bits work. So don't expect it all to sink in at the first time, or even after that. And as I say, I would strongly recommend Sammy's materials, which the book that she's developed off the back of this, which I think will be a really useful reference point for you. Obviously, some of it in 2 weeks' time after our break next week. There'll be one more SimPy session where we'll go into some of the stuff that you'll see covered in Sammy's book. Some of that will be in the next session, but some of it in there we don't cover in the main lectures, so it'll be really useful sort of reference material. All I will say is that don't panic when you first see SimPy. We've actually changed the way we teach SimPy this year. So we used to follow the way in which the SimPy tutorial does it, which is to show you one way and then show you how to translate it into an object-oriented format. That's the way we've done it for a few years, and it's more accessible at the start, I think, it would be fair to say. The problem is nobody then ever uses the object-oriented way because it's too difficult to then try and translate it. And so people end up with quite messy procedural models. So the way we've done it this year is to go straight into the object-oriented way of doing it. So you only see one approach. But so there will be a sort of, it's a bit of a steeper learning curve, but once you get it, you know that that's how you structure all your models. So hopefully that will make it easier in the long run. Hopefully, fingers crossed anyway. So obviously I did, before lunch, we didn't quite get a chance to go over generator functions, which I'm going to whiz through very quickly now. Let me just switch back, to the other slides. Because generator functions are fundamental to the way in which SimPy works. So it's good to understand how these things work, because they're a little bit odd compared to the kind of functions that you've been used to. As I said, SimPy is built around these concepts in Python known as generator function. It's a really neat feature of function that allows you to have this special kind of function that works a bit differently to the kind of functions that you've been used to seeing so far. So the kind of functions we've looked at in the Python training, standard Python functions, you're hopefully getting a bit used to them now. You write a function definition and then you call them, and your function does something. And when you call that function, you provide it with potentially some inputs, although you don't have to, depending on the function. And it does its thing, and then it finishes, and sometimes, very often, it'll return an output of some kind. But when we run that function again, if we call that function again, it'll start again from scratch as though we never called it. Okay, that's how you're used to seeing functions and using functions so far. And that's how a standard Python function works. But a generator function in Python is a little bit different. So a generator function remembers where that function was and what it was doing when it passes control back. And this is known as retaining its local state. And the advantage of that is that it means that it can continue where it left off. And because of that, that means it can be used as a powerful iterator. And an iterator, you've heard me talk about iterable objects and iterators a little bit during the Python training. Basically, iterators just things that you can step through, iterate through. And so you've already used iterators, different kinds of iterators. You've used for loops and while loops. They're examples of iterators. You go through, it does something, and then you go back round and you do it again. A generator function is a type of iterator, just like a for and a while loop, and that's different to a normal function. Now, generator functions are so useful because it allows us to maintain this local state. It allows us to get the function to remember where it was, to pause, and then we can come back to it, and it'll carry on where it left off. And that's particularly useful if we want to work with discrete event simulation, because we can do things like we can remember how long until we generate the next entity, or we can remember where a particular entity is in a pathway. So where is our patient in the pathway right now? So let's look at a really simple example of a generator function just to see how they work. There's a copy of this in your lecture examples folder for the 2A session, the one we were using this morning. And this is just a really simple example that I've made up that demonstrates what a generator function looks like in Python. So I've just made up a function here, and you'll see it's defined in exactly the same way as a normal function. We use the def keyword, we give the function a name. I could give it some inputs, I don't need to here. And all this function is going to do is it's going to start by setting a variable that I've called count. It's going to start that at 0. And then I've basically got an infinite loop here, a while loop. If we use while true, that just basically means keep going indefinitely. And all I'm going to do in this function is add 1 to this count, okay? And so far, this is all looking like a standard function. The bit that distinguishes it and identifies this as a generator function as opposed to a standard function is that rather than use a return keyword to pass control back to the main Python code, here I'm using a yield statement, okay? And yield is, I mean, without getting into the details, it's a bit like return, but it basically tells the function to freeze in place and pass control back, and then when we jump to the next step of this generator function, it'll carry on from that point. It won't go back to the start, it'll carry on where it left off. Now, a standard function doesn't work like that. If you were to write a standard function and write a return statement here, the next time you call that function, it would start again at the beginning. And so count would go back to 0 each time. So that's how we define a generator function, exactly the same way. It's just we use yield instead of return, and that will identify it as a generator function. When we call them, we also call them a little bit differently. So you're used to, with a standard function, we call the function by giving its name. We open brackets. If there's any inputs, we put them in the brackets. And then if it's going to return an output, then we have a variable assignment. So we would say this equals that. So that basically it says, you know, that any output from this function, bung it in there, basically. That's what you've been used to so far. But with a generator function, they work a bit more like the object-oriented approach that we looked at last week. Basically, we create an instance of our generator function. And so here, I've created an instance of the generator function. I've just called it my generator. It's not particularly imaginative, but it'll work. And I said my generator equals keep count generator. So now I've got an instance of this generator function. And I can create, just like object-oriented code, I can create as many instances of that as I want and work with them all independently. And hopefully your mind is now starting to think, oh, that could be quite useful if I were to create a generator function for each of my individual patients all going through my system, for example. And that's basically exactly what you're going to do in the SimPy structure. We'll see examples of that this afternoon. So I've created an instance of my generator function here, and then I'm using a next the next function here. Basically, what the next function does is it allows you to move to the next element of an iterator. Now, because a generator function is a generator function is a generator function. Yes, it is, but it is also an iterable object, which means we can call next on it, and it basically says, right, move to the next bit. Don't worry too much about next. You're not going to use that for SimPy. This is just to demonstrate a raw generator function in Python. SimPy deals with it slightly differently, as we'll see. But here, what I'm doing is I'm basically each time I'm telling the generator function to run, but move to the next bit. And I've put it here. I've put get it to print out the output of this generator function. Now I've put in 5 separate lines of code here that all say the same thing. I could have obviously put this in a for loop, but I just wanted to really spell out what's happening. So the first time we've created the instance of the generator function. When I use the next function on that, pass in my instance of the generator function, it'll start. So it'll run it for the first time and say, right, count equals 0. It enters this infinite loop. It adds 1 to count. So count is now 1. Then it gets to this yield keyword, at which point it passes control back down here. So control is passed back to the main Python code, and we told it to print out the output. So the first number is 1. Then when I tell it to go, you call the next function again, rather than starting at the beginning like a normal function would, this one says, okay, well, I was here. Right, let me go round again. So it resumes from this point. Well, at this point, I'm in an infinite loop, so I need to go back up here. Not there, but here. Back in, because I'm still in this loop. So I add 1 to count. I then yield, so I pass control back. But of course, and I print out the output, so count is now 2, etc. And each time I go round, I'm starting from this point, not from the start of the function. Okay, and that is what differentiates a generator function from a standard function in Python. And they're really useful when you want to do stuff like this. But the most common way you'll be using them is via SimPy, which uses them a little bit differently. But that's the basis of how SimPy basically works. So in SimPy, we basically use generator functions in 2 different places. We use generator functions to model, this is where it gets a little bit confusing, because we talked this morning, there are things in discrete event simulation called generators. There are arrival points. So unfortunately, the names aren't particularly helpful here, but the generator functions can be used to model our discrete event simulation generators, i.e. our arrival points. But they can also be used to model the individual journey through our system of each entity. So we have a generator function for each arrival point, each discrete event simulation generator, and we have a generator function for each entity going through, or an instance of the generator function for each entity going through the pathway. So let's imagine we're modelling patients in a patient pathway, which is what a lot of you are going to be doing. So for this bit, to model the arrival points, the generator function will basically create a patient. It'll then set them off on their pathway. Then it'll freeze in place for a amount of time that represents the inter-arrival time to the next patient. So it waits then, and then when control is passed back, that time has elapsed, and it continues where it left off. So it then generates the next patient. Then it works out how long to the next patient, freezes in place, and then when the control's passed back, it generates the patient, then waits and keeps going round and round in this loop. For this bit, where we're using generator functions to model the individual journeys of each entity through our pathway, then the generator function will essentially request a resource. It'll say, okay, I need a nurse now. And it will freeze in place until that resource is available. That models the queue. Okay, that's emulating the entity waiting for the resource to become available. When the resource is available, it will then freeze in place again for an amount of time, our activity time, that we've randomly sampled, but it freezes in place with the resource. And that represents the activity. So in other words, it's now freezing in place, but it's got the nurse with it, it's got the reception desk with it, or whatever it may be. And then once it's done that, and once it's finished, that the patient has then finished with that activity. It'll then either move on to the next activity if there is one, or if there's nothing else, then effectively that becomes a sync and it leaves. Okay, so this will make more sense when you see it, but basically that's the general pattern of SimPy. This is how SimPy works. Okay, so you have arrivals where you use a generator function to create a patient, then send them on their way. And the way you send them on the way is by creating an instance of one of these down below, and you'll see how that works. Then it freezes in place. It says, okay, there's 10 minutes till the next patient. Let me know when 10 minutes have elapsed, so it just waits. Then when controls pass back to it after 10 minutes, it will then say, okay, great, I'll create the next patient, send them on the merry way. Right, the next patient is in 8 minutes, freeze, and that's what the arrivals are doing. And then the generator functions for each type of journey are basically just saying, okay, I need this resource, freeze, wait for it to be available. When it is available, then grab the resource, freeze for the amount of time that it takes for the activity to happen. So I'm going to spend 3 minutes with the nurse, I'll freeze for 3 minutes. And then once that's finished, the nurse is released, the patient's released, and they go on to the next bit. That's basically fundamentally how SimPy works. And before you panic, it's got lots of the advantage of using SimPy is it does all this control stuff, all the clever stuff in terms of scheduling. It's doing in the background and passing control back and forth. It's doing all that for you. So fundamentally, this is what you've got to worry about. Okay, this is where we would have stopped for lunch. Sammy, can I just ask, are there any questions about generator functions that have cropped up in the chat before we move on?
No, I think we're good. If anyone's interested in having a look in the chat, we've got a discussion about the generator functions, but I don't think we need to share it here. You has actually just asked, is there a way to animate the SimPy results? Yes, there is. It's something I've been working on in the last couple of months, but I haven't managed to release the package yet, but it's something I'm hoping to be able to do a masterclass on. So we will have that potentially at the beginning of phase 2, and it will go into the book when it's ready as well.
Yes. So the answer is not natively, no. But all you need to do is employ a Sammy, and she comes up with the solution within the first 4 weeks, I think, of joining us. Really nice. Sammy's done some really nice work on creating visual outputs from Discrete Event Simulations. So you're in the training here. You're just going to see basically standard text outputs. You won't see any animations or anything. But Sammy has been working on this package that you can then basically bolt on, and it will then show it animated. Okay, so we're looking at the engine room today. But yeah, Sammy's done some great work, which I think you'll all appreciate. In fact, anybody that went to the open day and went to the DES workshop will have seen a glimpse of that. That was actually one of Sammy's animation engines running. Cool. Okay, so that's generator functions. So I will now skip back to this afternoon session and let's start talking about SimPy. So what is SimPy? It's a Python package, free and open source, of course, because it's on this course, and it allows us to create discrete event simulation models very, very flexibly. And as I mentioned, it's built around this idea of generator functions. Okay. Now, just to flag up, SimPy does have some tutorials and reference guides on its website. I think it would be fair to say, I mean, admittedly, I haven't looked at them in a while. Certainly, so I used them to teach myself SimPy, but I already knew discrete event simulation. So I was, as a team, we were transitioning from a commercial piece of software called Simulate, which we used to use because it's very nice, but costs thousands of pounds. And actually, you can't do a lot of stuff in Simulate, where you can in SimPy. It was pretty good for that, but it kind of already requires you to have some base level of understanding. It's almost designed to migrate you to SimPy from something else. The tutorials aren't that extensive. They can be useful, but hopefully as an accompaniment to this and Sammy's materials, they will be useful. So we've designed this training to be, I know nothing about discrete event simulation, tell me about that and how I build these things in SimPy, which is how we've approached it. SimPy is a package that does not come with the Anaconda distribution, so it's one we have to install, which you can install using pip install SimPy. But of course, we know as good data scientists, what we shouldn't do is just install everything in our base environment, because that's just a recipe for disaster. You'd probably be fine with SimPy because it's pretty stable and it hasn't been sort of worked on for years. They just got it right and working, and it's all good. But it's not a good practice to get into. So for the work you're going to be doing this afternoon, and indeed any discrete event simulation modeling work you want to do, you can use the DES environment, which as part of session 1D, some of you managed to do that as part of exercise 5. Some didn't manage to get it working. If you didn't get it working, hopefully you've seen the instructions to install it from the YAML file, which we've supplied as part of this repository as well. But however you've got the DES environment onto your machine, and I know Sammy's put out alternative instructions for using virtual environments as well if you're not using Anaconda. When you do the exercise this afternoon and when you do any discrete event simulation work, you will need to switch into that environment. That is not the case if you're using Colab. You can just install it into your session, basically. Before we look at how we're going to put together one of these SimPy models, there's a few things that we need to get our heads around first that'll hopefully make it a little bit easier to understand some of the things that I'm going to talk about. Some of these things are, if you're an operational researcher, you'll be used to these concepts, but if you don't come from that world, which most of you don't, then it's worth explaining these things first. So the first thing to talk about is about the concept of simulation time. So SimPy simulations run in time units. Okay, that's their unit of time, and these units of time can represent any real-world amount of time that we like. Okay, it will SimPy just thinks of them as units of time. You don't tell it these represent minutes or days or weeks. It just gives it to you in units of time. So how you build your model, you need to decide what your units of time represent, and you can make it anything you like, but you have to be consistent within the same model because you're going to express everything in time units. So you need to decide what is the unit of time I'm going to use for this particular model. So in reality, what you need to do is decide on the lowest level of real world time that you need to represent in your model. So for the vast majority of things you will be doing, you will be modeling probably patient pathways or service user pathways where people turn up for a service and things happen to them and then they leave. That's most of what you'll be doing, in which case you'll probably, in most cases, want to use minutes as being your time unit. Seconds is far too high resolution that you don't express things in seconds for something like that. Hours is probably not detailed enough unless all the processes are very slow. But in most cases it'll be minutes. However, that doesn't mean that will be the case for all models you design. You need to think about how this relates to your real world system, and you may have pathways where we measure time in days or weeks, and those may be your units of time. Just be aware, if you've got a model where your time units are in days, for example, it's more difficult to then represent things as and I've got a process here that takes an hour. Okay, so you need to think about it, you still have to express it in terms of days, so just be aware of that. So in our emergency department a fictitious example we were looking at earlier, our time units would probably be minutes. So we'd specify everything in minutes: the time inter-arrival times, time between patients arriving, how long they spend with the nurse, how long it takes them to get treated, etc. Now I'm just putting in this little asterisk here because I said that SimPy runs in time units. Strictly speaking, that's not true. SimPy doesn't. When I say that, you're probably imagining that SimPy has this kind of clock and it jumps from time unit 1 to time unit 2 to time unit 3. That's not technically how it works. Instead, what it actually does is it has a very powerful scheduler, and it schedules events and it will jump ahead to those things based on its scheduler. You don't need to worry about that. SimPy deals with it. But I just wanted to flag that up because I didn't want you thinking that it's technically working as, okay, I moved to time unit 1, is anything happening here? No, we'll move to time unit 2. When we got into agent-based simulation, later in the course, where we use a package called Mesa, that does work in that way. You literally go through one time unit at a time, and it says, okay, what do I need to do on this time unit? But that's not how SimPy works. It works in a slightly... It's got all sorts of weird things that it does underneath the bonnet. But as I say, you don't need to worry about any of that. Just be aware that that's how it's working. Also, I flagged that up because you'll often see your simulation time referred to using floating point numbers. So you can ask it for the current time in the simulation, and the answer might be 3.6247. You think, what? That doesn't make any sense. But it does if you realise it's not ticking over time unit 1 and time unit 2. It's not doing that. It's saying, okay, I've sampled 3.7 minutes to the next event, so the current time is 1.6, so it'll be 2.1 minutes till the next event. That's how it's working. Another important concept to understand when you're doing any simulation modelling, the concepts of runs and trials. So in a stochastic model, which is most of the models that you are going to be building on this course, with I think only one exception, which is system dynamics. We'll talk more about why that isn't stochastic when we get to that. But discrete event simulation models tend to be stochastic. You tend to have an element of randomness to them. Virtually all discrete event simulations will have a concept of variability. Because of that, if we've got any stochastic model, we shouldn't draw any insights just from running the model once and then saying, okay, it's predicted that the waiting time will be 3 minutes if we do this. That's really bad practice. And that's because every time you run the simulation, it's going to generate effectively random numbers. It's pulling them from a distribution that is mimicking your real world variability, but it's still random. Okay, so you could end up with a run of bad luck where in that particular run it sampled really long activity times, for example, long times with the nurse or whatever it may be, or unusually long inter-arrival times, which might be a run of good luck where essentially patients are not coming in very frequently. And that may not be very representative. So we don't tend to just run them once and take the result from that. That's not how we deal with stochastic simulations. So instead, when we've got a stochastic model, we have to run them lots and lots of times. And then we take sort of summary stats over the results from each run to try and get a better idea of what it looks like. So we might run it like 100 times, sometimes even thousands of times, and say, okay, well, we've run this version of our system, we've run it lots and lots of times, and on average it's saying the waiting time will be about this. That's how you run a stochastic model. Don't just run them once. That only applies to stochastic models. If there's no variability in your model, you don't need to do that, because a deterministic model, which is the opposite of a stochastic model, there's no variability, so the results would be exactly the same every time. There's no randomness, so you only need one run. But most discrete event simulations that you will build will not be deterministic. So a single run of a model for a particular simulated period of time. So let's say you decide to run, you've built a model of an ED and you say, okay, I'm going to run it for, I'm going to simulate a week of ED arrivals. That running 1 week's worth once of simulated time, that would be known as a single run. And then what you'd want to do is then run that week's worth lots and lots of times. You'd have, 100, 1,000 representations of a week in the life of this ED. And so a batch of multiple runs with the same parameter values that you're feeding in is known as a trial. Okay, so a run is a single run of the simulation for however long you set it to run for, and a trial is basically a batch of runs. Okay, so that's just two things I wanted to really flag up before we get into the details of SimPy. So let's start by looking at a really simple discrete event simulation model and see how we'd build it in SimPy. Okay, so this is an incredibly simple discrete event simulation. Arguably, you can't get much more simple than this. We've got a single generator with patients arriving. There's one activity, a nurse consultation that needs a nurse, and then a sync where the patient leaves. So literally, patient comes in, queue for the nurse, see the nurse, leave. That's the system. So we're going to see how we would build this in SimPy. And as I mentioned earlier, particularly because of the way we're going to go straight into the object-oriented structure, you might look at this and think, wow, this seems complicated for that. And you'd be right in some ways. But of course, your real models won't look like this. They'll be likely much more complicated. And the beauty of this is that if you follow this slightly complex looking structure initially, then when you need to add more information in, it's really easy. You just follow the structure and add and bolt more bits on. And so it makes it much, much more elegant for more complex models, which are the kind of models that you'll realistically be building a lot of the time. So I'm going to be talking through in these slides the SimPy example 1.py Python script, which is in your lecture examples folder for this repository for 2B. You might want to have that open. If you get distracted by having lots of screens open, don't worry. I'm going to talk through the code here. But if you did want to open, that's the code I'm going to be talking through. Okay. So the first thing to say, and there are different ways of doing this, but this is the way that I'm teaching, and this is the way I use when I'm developing SimPy models. We're going to structure it in an object-oriented way, and the way I'm going to do it is by having four different types of classes. We may have more than 4 classes, as we'll come on to. And these are basically our 4 classes, and we'll have 4 classes for this simple model that we're developing here. So the 4 classes are going to be as follows. We're going to start with a class called G, lowercase g. Now this is a special kind of class that will basically store our global level parameter values, and you'll see some examples of what they might look like. So the kind of parameter values you want to feed into the model, that's where they're going to live in this special G class. Now, after the object-oriented programming last week, this may seem a little bit odd. Unlike most object-oriented programming classes, we're not going to create an instance of the G class. That's why it's lowercase. We're going to refer to it directly. We're not going to create a class and then say, I want an instance of the G class and then work with it. We're just going to say, here's the G class, dump in our parameter values, and then we just refer to it, almost like a little database. Okay, so that's why it's a lowercase g. It's a little bit odd, but that's the way we do it. Then we're going to have a class called patient in this case, but what you call it will depend on what your entity represents. So in the model we are developing here, we've got patients coming in to see a nurse. So my entity type is patient, so I've called my class patient, and this represents our entity. Okay. So our entity in this case is patients, and they carry with them information that we can record to and or read from. And you remember from the object-oriented programming that we did last week, that's basically what attributes are. They're carrying around information with them that can change over time. And so in our case, it might be that the patient has an ID, They might carry information about how long they spent queuing after they've queued, what their condition is, priority level, all that kind of stuff. In fact, most of you, when you were doing this morning, picked up on that would be a really useful thing to have in as attributes against the entity. So well done, because that's exactly how it's going to work here. Now, obviously, in some cases, you're going to need more than one type of entity. So if you've just got a simple model like this, where you're just modeling patients through a system, then you only need one type of entity. But if you've got more than one type of entity, you'd need a separate class for each. We also need a model class, and the model class is basically the main one. This is the big one where all of the stuff that represents the system that we're modeling, so in our case, our very simple clinic, that's where it all goes. So that'll have our generators that are creating new patients. That'll have the description of the patient journey. And that's where these something known as the SimPy environment, which is basically just where everything lives within our SimPy model, that's where it'll be kept in the model class, okay? And then lastly, we've got a class that I've called trial, and basically this class is going to represent a batch of runs in our simulation, and it'll have various methods that allow us to run a trial and get out the results and all that kind of thing. So we just talked about runs and trials, and we said basically a trial is just a batch of runs. So I'm going to create a class that represents a batch of runs to say, okay, I want to run a trial so that you run it X amount of times with this combination of parameters. But before we get into any of the classes, what do we need to do first when we're writing Python code is we need to import the packages we need. We will start with our import statements. So for when we're doing SimPy modeling, we must import SimPy, otherwise it's not going to work. So we have to import SimPy, and then whatever else you import is going to be very much down to you and how you've designed your model, but it's likely you are going to want at least these other two as well. The random library, because we're going to use the random library to sample from exponential and log normal distributions, which is how we're going to get our interarrival times and our activity times. And pandas, because pandas is beautiful and it'll allow us a neat way to store our results in a table. Okay. So let's start going through these classes one at a time. Okay, so let's start with the G class, which is the weird one, where we're not going to create an instance of it, we're just going to refer to it directly. And the G class is going to store all of our global parameter values, okay? And that means it's an easy place where we can just go into G and we can change various aspects of our simulation to see what might happen if we change bits of how it runs. So we don't want to be ferreting through our code trying to look for where we stored the number of doctors or the number of the opening times of the clinic or something like that. We just want to have them all in one place. So the G class allows us to do this. And it allows us to do things like store values for the that will define our interarrival time distributions. So things like how often on average are they coming in? What's the standard deviation of that? Values to define the activity time distributions. So how long they're going to spend on average with the nurse, what the standard deviation is, etc. The number of each type of resource that we've got, so how many nurses, how many doctors, all that kind of thing. How long we want a simulation run to be, and the number of runs within a trial. So how many runs will make up a trial. All that kind of stuff will go in our G class. And as I say, we will refer to it directly. We won't create an instance of it. So here is the G class for our very simple patient comes in and sees a nurse model. Okay, so here I've created class G, lowercase g. I use my colon as normal, but unlike the classes you've seen before and where you will see for the rest of them, here, because it's a special kind of class, we're just going to dump in some variables and their assignments. Okay, so there's no constructor, nothing like that. We don't need a constructor because we're not constructing anything. We're not creating an instance of this class. We're just, it's a dumping ground for our parameter values, basically. So here I've set up a variable that will store our patient inter-arrival times. I've said every 5 time units. My time units are going to be minutes, I've decided here. The mean consultation time is going to be 6 minutes. So already the astute will observe there might be an issue with this system. Patients are on average arriving every 5 minutes, but on average, a nurse takes 6 minutes to see a patient. So that's probably going to indicate you're going to have some queues building because patients are arriving slightly more frequently than they can be seen. I'm going to store my number of nurses, which is going to be 1. How long I want my simulation to run for. So 120 time units. Remember, I've decided my time units represent minutes. So 2 hours, basically. And then the number of runs. I'm going to run my simulation 5 times. Okay, so that's the G class. That's pretty straightforward. Let's move on now to the patient class, or whatever your entity is. So if your entity is a blood test result, it might be called blood test, or whatever it is. But let's just, for the moment, imagine we're building our little simple model. So here we've got our patient class, which represents our patient entity. And we store attributes here that the patient is carrying around with them that are unique to that patient. So a nice way to think about this is to imagine you've got a patient literally carrying around a clipboard with their information. You probably won't need things like name and stuff for a discrete event simulation model, but it may have an ID. They may make notes on how long did I spend queuing up for the nurse, how long did I spend queuing for the doctor, what's wrong with me, all that kind of stuff. But in our simple model, we're just going to have a patient that's going to carry 2 pieces of information with them. They're going to carry an ID so we can identify that patient, and how long they spend queuing for the nurse once they have, once that's known. But as I say, in more advanced models, you could have all sorts of things like condition, their priority, what the probability is they'll go down a particular branching path, all that kind of stuff. So here is my patient class for this very simple model. So I define my class called patient, and this looks much more like the classes you're used to from last week. So I've got a constructor. So here's my constructor. So this basically says that I need to, when I create a new patient, I'm going to have to give them an ID. So I'll create a patient, and it'll be, this one is patient ID 1, for example. And all the constructor is going to do is say, okay, the ID that I pass in, that will become your ID. Remember, self basically says store it against me as an instance of the class. So that I want the patient ID I give you to be your ID, and you're also going to have a piece of information which will be the queuing time for the nurse, but at the start you haven't queued yet, so I'm going to set that to 0. Okay. So just those 2 pieces of information I'm going to give it. I could do whatever I like here, but that's what I've chosen to do. Okay, then we move on to the big one. So the model class is basically where most of the things live. So let's start by talking about the constructor for the model class. So the constructor for our model class is basically going to set up our SimPy environment. Remember, we said that's where all our components live. It's going to set up a patient counter, which we're going to use to give our patient a simple identifier, a simple ID. So that we basically say, okay, first patient comes in, that's patient 1. Second patient comes in, we'll call them patient 2, etc. We'll provide in the constructor, it'll set up the resources we need. We only need 1 resource in our simple model, it's just a nurse. And I'm also going to create a pandas data frame that will store per patient results for a single run of the model, so that we can easily access, okay, patient 3 spent 7 minutes queuing for the nurse, whereas patient 4 only spent 2 minutes queuing for the nurse. And we can store all that in a pandas data frame, and I'll set that up in the constructor for the model class. So let's have a look at the constructor for the model class for this very simple model that I'm developing. So here is my class model. This is just the constructor we're looking at for the moment. So here is my constructor. So here I'm passing in, whenever I create a new model, I need to pass in the run number. So basically it'll say, okay, you are run number 27 of this model. So the first thing I'm going to do here is I'm going to create a new SimPy environment. And this is how you create a SimPy environment. You simply say SimPy.environment, and that creates a new instance of the SimPy environment. It's literally that simple. And we're going to store that within self.env. So we always use env. You can technically call it whatever you like, but env is the convention. That's where we'll store the environment, and it's going to be a property, an attribute of the model class. So I'm saying self.env. So model, this is your environment. Then I said I want to, in my model, I'm going to have a little simple patient counter, and that's how I'll determine what each patient's ID is. So I'm going to start by creating that patient counter, and I'll start it at 0. Then I'm going to create my resources. I've only got one resource here, which is a nurse, or one type of resource, I should say, which is a nurse. So I'm going to create a nurse. I can create a nurse in create a resource in SimPy just by saying SimPy.resource, and then I pass in two things to create a new instance of a SimPy resource, which gives me a type of resource. I'm going to pass in the environment in which it will live, which is the thing I've just created up here, self.env. And I'm going to pass in the capacity. So we say capacity equals, and then this is where I specify how many nurses I want, okay? Now, because I've I've defined the number of nurses in my G class, I can just say G dot number of nurses. That's where I stored it. And it'll go to the G class, say, okay, yeah, he wants 2 nurses, 1 nurse, whatever it may be. So I could just hard code it here, but this is the advantage of using the G class. It means that I don't have to go looking through all this when I want to change the number of nurses. I just go to my G class and say, okay, I'll change that to 2. So I'm going to store that as a SimPy resource, and I'm going to call that self.nurse. I'm also going to store the passed in run number, and I'll call that self.run number. And I said I'd create a pandas data frame that's going to store the results for each patient. So we can look at each patient's results as they move through the model. So I create my new pandas data frame, just as you used to doing in the pandas session. I created a new pandas data frame, and I've created these columns with these initial values. So first patient ID, or patient ID 1, queue time for the nurse will be 0 to start with. Time with the nurse will be 0. So basically for each patient, we'll be able to look at their ID, how long they spent queuing for the nurse, and how long they spent with the nurse. So that's really useful if we want to look at individual patients then. And then down here I just set my, I'm going to make sure that patient ID is unique, because I'm using a simple counter. So I'm going to use that as the index. I don't have to, but I've decided to do that here. So I can look up patient 72 and then I'll get the results. And then lastly in my constructor, I'm going to create... Oh, sorry, I think somebody was unmuted. Lastly, in my constructor, I'm going to create an attribute that is going to store the mean queuing time for the nurse across this run of the model. So across all patients, so this is the model class. Remember, each patient has got a little clipboard that says, I spent this long queuing for the nurse. Whereas this is the model class, and it says, okay, across this run of the model, this will store the average across all of my patients. How long on average did they spend queuing for the nurse? So I just default that to 0 by default. So that's the constructor I'm going to use for my model class. Now we need to create some other methods, and the first one I'm going to do is the generator function that is going to represent our discrete event simulation generator. So this goes back to what I was talking about at the start. This is going to model our arrival point of patients coming into our clinic. And we're going to use a generator function to do that. technically a generator method, if you like, because it's in a class, but there we are. So here's basically what it's going to do. And it's going to keep repeating this forever. Well, until the simulation stops running. It'll just keep doing this. I'm going to get it to increment the patient counter to get the ID for the next patient. It'll then create a new patient. And remember, we've got a object-oriented structure, so it'll create a new patient object. And it'll say, here you go, here's your ID. Then it'll start up an instance of the generator function that we're going to write in a minute that will represent their journey through the system. And it'll chuck that patient into that generator function. Then it'll sample the time until the next patient arrives, so it'll sample into arrival time. It'll then freeze in place, because it's a generator function, it'll freeze in place until that time elapses, and then once controls pass back, once that time has elapsed, it returns to 1. Okay, so each time round it's saying, right, give me the next patient ID, I create a patient, here's your ID, I'm going to create a new journey for you, I'll chuck you into that journey, then how long until my next patient? Okay, I'll freeze in place until then. Then when controls pass back, it goes round again. Creates the next patient ID, creates the next patient, chucks them into the journey, etc., etc. So what does that's basically what it's going to do. How does that look like in code? This is how it looks. So remember, it's a generator function, so we're going to see a yield keyword, and here it is down there. We'll come to that in a moment. So I've called mine generator patient arrivals. So you probably want to indicate, this is the name convention I tend to use. If it's a generator as in an arrival point, then I tend to say generator as the first word, and then the rest of my words used to describe what type of arrivals this is generating. Now, in this case, we've only got one generator, but what if I then wanted to expand my model and had 2 different ways in which patients can come into the system? So it's always worth naming stuff to allow for expansion easily. So generator for patient arrivals, okay? This being a class method, I have to pass in self, remember, even if I'm passing nothing else in. And then I'm going to create an infinite loop. Remember, I want all this stuff here. I want to keep doing this forever until the simulation stops. So within an infinite loop, so while true, increment my patient counter. So take the patient counter that I've set up in the constructor. I refer back to that, add 1 to my patient counter, then create a new patient using the patient class. And remember, when we create a patient, we said we'll give you an ID, and the ID I'm going to give you here is going to be whatever my patient counter currently says. So if you're the first, you will be patient number 1. So that new patient is now referred to as P. This bit here is where we tell, we say self.env to get to the SimPy environment, and we call the process method of the SimPy environment. Now, you don't need to worry about the details of this, but basically what we're doing here is we call env.process, and then we pass into that the generator function that we want to start processing. Okay, so this is a bit weird at this stage because I've said self.attend clinic. I haven't yet written self.attend clinic, but that's the one we're going to look at in a moment. That is the name of the next generator function that I'm going to write, which describes the patient's journey. Okay, so I've called it attend the clinic. So it's a bit, you have to kind of write them knowing what you're going to call the next thing. So what this slightly weird looking line of code is doing is it's telling SimPy, I want you to start up the generator function that defines a patient's journey, which I've called attend clinic. I want to chuck the patient I've just created into that generator, and I want you to process that. And by calling process, SimPy is doing all its magic in the background with the generator functions. That's why you don't have to use the next keyword or anything like that. So then once it's done that, it just now needs to say, okay, well, when's the next patient coming in? So here is where I'm going to sample from an exponential distribution. So you saw a glimpse of this last week, I think it was, or it might be the week before, when I told you to use the random.expovariate method. Basically, expovariate is a method within the random library that allows us to sample from an exponential distribution. Okay, so we're dealing with arrivals here, inter-arrivals, so we're going to use exponential. We're also going to use, just to flag up, we're going to use exponential distributions for the moment for our activity times as well, just to keep it simple. As I mentioned this morning, that's a good starting point. We'll show you in the next session how you then translate that to a log normal. But for now, we're just going to use exponential. So this basically says sample from an exponential distribution, and remember we have to pass into an exponential to expovariate. We have to provide lambda, a value called lambda that defines an exponential distribution, and lambda is just 1 over the mean. Okay, so that is basically says sample for an exponential distribution where lambda is 1 over, and then this is our mean. So this is our, if patients are arriving every, what was it, 5 minutes, I think? Yeah. Patient inter-arrival time, we set up on average, patients arriving every 5 minutes here. So we can access that here by saying grab the average inter-arrival time. So what that does is it says patients are arriving on average every 5 minutes, but put that into an exponential distribution and randomly sample from an exponential distribution that is defined with a mean of 5 minutes. So that will give us, it'll randomly pick a value, randomly sample a value, that will then be stored here. So it might pick 5 minutes, but it might pick 4 minutes. Well, it'll pick 4.72417 minutes. The chances of it picking 4 on the, because of the way that this works. So it's sampled the time until the next patient. Then all we need to do is to get it to freeze in place until that time has elapsed. So here I call a yield statement. This defines it as a generator function. And I say self.env.timeout. So we call the timeout method on the SimPy environment. And that basically says freeze for this amount of time. And the time I pass in is whatever time I've sampled. Okay, so it looks more complex than it is, partly because I've got comments here to explain everything. But if you look, there are just 5 lines of code in this infinite loop. It's just saying, give me the next ID, create a new patient with that ID, chuck them, start up a generator function for the pathway and chuck this new patient in it, then randomly sample when the next patient's going to come in from an exponential distribution, and then stop, hammer time. Okay. So then when control is resumed, and that time has elapsed, so if it's 7 minutes that it's sampled till the next patient, when SimPy, this is why we use the SimPy timeout thing, SimPy deals with it for us, when SimPy identifies that time has elapsed, because this is a generator function, it'll start again from here. So it goes, okay, right, where was I? I was here, right. Back around the while loop. So add 1 to the patient counter, create the next patient, chuck them down the pathway, what time's my next patient coming in, stop. That's basically all it's doing. That's all it's doing each time. So that's the generator function for the discrete event simulation generator for our arrivals. Let's look at the big one. So this is the other generator function, the one that's going to represent patients going through each step of our system. Okay. Now, fortunately, we've only got a very, very simple system here where we've just got patient comes in, see nurse, leave. So here's how it's going to work. It's going to record, the first thing it's going to do is record the time that the patient started queuing for the first activity. It'll then request the resource for that activity. It'll wait until that resource is free. Once the resource is free, it'll then keep hold of that resource until it's finished with them. Then it'll record the time it finished queuing and calculate the queuing time. It'll sample how long it spends in this activity. It'll then freeze in place with that resource, with it, for that amount of time. And then if there's another activity, it'll do the same again with that activity. If there's not anything else, essentially it becomes a sync and it just leaves. So basically patient turns up, right, what time did I start waiting? okay, I need a nurse. I'll wait for a nurse to be available. Time's ticking away. Once the nurse is available, I'll make a note of what time that was so I can calculate how long I was waiting. Okay, now I will randomly sample from my distribution how long I'm going to spend with the nurse. Then I freeze with the nurse in place and neither of us can move. We are both locked into this activity for that amount of time. And then I release. Okay. So what does that look like in code? And this spans 2 slides just to flag up. So I've called mine Attend Clinic. Remember I said that was the name of it I gave up here when I'm pointing to my monitor. That's not really helping you. When I created told this generator function to start up when I create a new patient, and I chuck them down through it, I said it was called Attend Clinic, so that's what I've called it here. And I define Attend Clinic by saying I will give you a patient object, because it needs to know the patient that is going to flow through this instance of the journey. Remember, you'll have 100 possibly or more generator functions, instances of this generator function that are all running at the same time for different patients. So this represents this patient's journey through the system. So I'll give you a patient. First thing I'm going to do, I'm going to record what time it is now. Okay, so I can get the current simulation time by using env.now, and because the environment's stored in the model class, I need to say self.env.now. That gives me the current simulation time. And I'll record that as the time I started queuing for the nurse. We're then going to say, we're basically we now need to ask for the nurse. And the way we do that is by using a with statement and using a request on the resource. Okay, so you're used to seeing with statements when we opened a file in the one of the earlier examples. We said, with this file in read-only mode, open it and do this stuff. We're doing the same thing here. We're saying, request a nurse, and with that request, do all this stuff. And that's what's going to keep the nurse in place, so it can't be used elsewhere. So we call the request method on the resource, which is our nurse resource here. And we're going to use an alias here, a conventional alias, we say as req. So we can now refer to the request as req. So the first thing I'm going to do is tell it, right, freeze in place until that can be done, until a nurse is available, until that request can be met. Once that request has been met, control will be passed back to this generator function. SimPy will do that for us. And so it will resume from this point. So when it gets to the next line of code, we know that a nurse is now free. So I can now record the time it is now and calculate how long I spent queuing for the nurse by saying, well, how long was that minus that? That's my queuing time. And I'll store that as my queuing time. I'll make a note of that. My little patient, he's got his clipboard there. He's writing down the queuing time for the nurse. I spent this long. Then we're going to work out how long I'm going to spend with this patient's going to spend with the nurse. And again, we're just going to use, for simplicity for the moment, we're just going to use the exponential distribution again. So I use exactly the same as I did in the inter-arrival times. I'm going to say randomly sample for an exponential distribution. But this time, the mean that I'm passing in is the mean consultation time that I've got stored in G. So that was the 6 minutes on average. How long does a patient spend with the nurse? It'll then randomly sample for an exponential distribution with a mean of 6. And then basically what we're doing here is I'm doing a little extra step where I've recorded. Remember the data frame that we created in the model class? I'm going to say, okay, well, dump in against this patient ID for their queue time for the nurse column. Store the patient's queue time for the nurse, so that we've got that stored, and also record the time that was sampled. This bit's a bit optional. It just makes it a little bit easier for you to see when you're starting out here. But in reality, you probably don't. And in fact, in the exercise you'll do this afternoon, I recommend you don't do that. So once we've done that, we're going to freeze the function in place for the amount of time that we sampled as being the activity time. So here's where I'll say we've sampled from the exponential distribution. We've worked out this patient's going to spend 4.7 minutes with the nurse. Okay, so here again, just as we did with the generator, with the arrivals generator, we're going to call a timeout in the SimPy environment, and we'll pass in that value we sampled. So that will then say freeze in place for that amount of time. Now, because, and again, apologies, this is spread over 2 slides, so it can be a little bit more difficult to see. If you're looking at the Python script file, you will see that this is all within the with statement. So that means here, when we're freezing, when we're timing out, we've still got the nurse. We're holding on to the nurse with us. And that's what makes sure the nurse isn't available for anybody else. When control is passed back, that means that time has now elapsed. And so the generator function will return here. Now, in our simple model, we've just got patient comes in, sees nurse, leaves. Okay, so we don't actually need to do anything else. If you just stop writing code, that represents a sink. The entity just disappears. They've left. There's nothing else to do. If we had another activity, this is where we will put it. And we'll come back to that in a second. Now, you might, in reality, want to add something in. You might want to have a little counter or something that says counts the number of patients that have gone through, and that's where you'd put it. But here I'm just saying, patients spent time with the nurse, great, they're done, finished. So let's just go back over that. When this generator function that describes a patient's journey says, I'm going to start queuing here, record the time, start my stopwatch. Now I want to request a nurse, and I'm going to freeze in place until that request can be met. Once I get here, the nurse is free, so I'll stop my stopwatch. I can calculate my queuing time. Then I'll sample how long I'm going to spend with the nurse. I'm going to store how long this patient spent queuing for the nurse and the time they sampled to spend with the nurse in my little data frame that I've got. And then I'm going to freeze in place with the nurse so that the nurse is locked in just as I am for whatever time I sampled to spend with the nurse. And then nothing else. So that will be the nurse is released. The nurse can go on to the next patient, and the patient has gone from the model. Hopefully this, I realise there's a lot to take in. So this will make more sense in the exercise when you have the time to basically create your own, and you'll be looking at all of this code. So the other method that I'm going to have in the model class is the calculate run results method. This method is basically just going to calculate the results, the average results, over a single run of the model. So here I'm just going to, for simplicity, I'm just going to calculate the mean, but you could do all sorts in here if you wanted to. But this says for a single run of the model, calculate on average how long patients were spending. So for one run, how long did the average patient wait to see the nurse? That's basically what it calculates. And the last method we need in the model class, I said this was the big one, and again, just for a fairly simple model, but the good news is more complex models don't expand up. We're going to create a run method in our model class. And basically there's 4 things the run method is going to do. It'll start up our generator functions, it'll start up the generator function that represents our arrivals. Now, we've only got one type of arrival here, but we may have models where we have more than one DES generator, i.e. more than one arrival point, in which case this is where we'd start them all up. Okay, so we use this process method again to start up a generator. Imagine winding one up and you're starting it up. So this starts up the generator. Remember, the generator for patient arrivals in turn starts up the other generator function, which for each patient, and chucks them down that journey. So we just need to start up the, this basically says start patients arriving. Then we're going to tell the simulation to run for however long we've defined in the G class. So we do that by calling the run method of the SimPy environment, and we tell it to run, and we say until equals, and then how many time units we want it to run for. And because we've got a G class, we've already specified that. And if you remember, we said 120 time units, 2 hours. Once the simulation has run, it will get down to this point. That will be a single run of the simulation, and we will then run the calculate run results method here, that one I just wrote, that will then calculate on average how long did the average patient spend in this run queuing for a nurse. And I'm just going to have a little bit down here where I'll then print the run number and say that was the result for this particular run. So that's the model method. That was the big one. There's one more class that we need, and that's the trial class. And the trial class, remember, just represents a batch of runs, because we don't want to run our model just once. We want to run it potentially hundreds of times. We're just going to run it 5 times here, but potentially hundreds or even thousands of times. So this trial class will contain methods to run a batch of runs, and it'll store and record and display results across that batch of runs. So let's have a look at the code. And this is, that is the whole thing. So here is my trial class. Here is my constructor for a trial. It basically creates a pandas data frame with these 2 columns, run number and mean queuing time for the nurse. So basically you've got a table in the trial that says for each run, if I've got 5 runs, there'll be 5 rows, and for each run it'll calculate the mean, how long the average patient spent for that run queuing for the nurse. I'm just going to have a separate method here that just prints out these trial results, just prints out that data frame. I mean, in real world models, you'd probably save them to a file, or as Sammy will show you when we get onto web app development, output the results to Streamlit. But for the moment, we're just going to print them to the screen. And then a method to run the trial, so to run a batch of runs. And the way this works is it'll say, use a for loop. It'll say for the run in range, the number of runs. So we've got 5 set up here. So that basically translates to for run in range 5. So do this 5 times. Create an instance of the model class, that big one we just created a moment ago. Pass in the run number to say, I'm running the model, and this is run number 0. Running the model, this is run number 1. So create an instance of that model class. Call the run method of that model class. This is where it gets a bit convoluted. So this was the run method of the model class, which basically said start up your arrival points, run the model, calculate the run results, and print out the results. So do that, and then store the results for this run in my trial data frame. Okay, and then once all of the runs have completed, i.e. you've got out the other side of this for loop, then print out the trial results. Okay, I appreciate there's probably, oh no, so there's one more thing. The final thing we have to do, so we've created a G class that's going to store all our global variables. We've created a patient class to represent our entity, created a model class that has all the big stuff, including the generator functions. And we've created a trial class that represents a batch of runs. The final thing we need to do, because they're just class definitions, is to set it all running. Okay, so outside of our code, after we've defined all of our classes, we'll create a new instance of the trial class, and then we will call the run trial method of the trial class, that thing we just ran here, just wrote here. That in turn will set off everything else in motion, because the trial class, the run trial method of the trial class will create a new model for each run of the simulation, and that model, it'll then call the run method of that model, and that run method in turn will start up the generators, which in turn will start up the other generators, and you have this kind of sequence of things that then all sort of kicks into action. Right, I'm going to stop there for a moment. There is more, but that is how we would create. That is basically. Let me switch over to the code. That is SimPy example 1. That is how we would create a SimPy model of that simple system. Sammy, are there questions?
So pretty good, actually. People are enjoying the game references. The main thing that I haven't been able to definitely answer is, can you request more than one copy of a resource, e.g. if you had a procedure that needs 2 nurses to do? I can think how you would do it with 2 resources that are separate. So for example, a doctor and a room. I think it's probably similar if you want 2 resources that are the same, but I'm trying to think if there's a more efficient way of doing it.
Yeah, I've been asked this before, so you can do it the longhand way of saying, grab me this and also grab me this, and it can be the same thing. I've got a funny feeling there is a SimPy shortcut, but I'd need to check that. I don't know offhand, but we can look at that. We'll put it in the book once we know.
Yeah, yeah, new chapter.
Yeah, but you can. Yes, you can do it. It's just whether there's an easier way than explicitly saying with this resource, and so you can nest with statements. So you can say with the nurse. Oh, and also with a bed, and then those 2 things get locked in together. And you can do that by saying with a nurse and also with a nurse. So you can do it that way, but I've got a funny feeling there might be a more efficient way of doing it. Yeah, well, I'll need to come back to you on that.
And I think that was the only question at this point.
Okay. So let me, before I there isn't too much more to explain. What you'll now see in a moment is that I'll show you how to expand that model, and you'll see actually it's pretty easy because you've got a lot of pain at the start, but then when you want to build the model up, it's fairly straightforward. Before I do that though, I'm going to run that version of the model that I've just created. So all this code here, which is why it took a little while to explain it, that's what I've just talked through. Okay, so you've got this file as well. I'm in my dev environment here, so I can run that. Let me just move this out of the way. And there we go. It's run it 5 times. Okay, and we can see in run number 0, the average queuing time to see a nurse was 14 minutes. In run number 1, it was 31 minutes. Run number 2, it was 2 minutes. You can see why you want to run these often hundreds of times, because what would you conclude? You'd conclude something totally different if you just went on the results of run 0 or run 1 as opposed to the results of run 2. This is why we do it hundreds and hundreds of times until we get stability, and we'll come back to that. So that is a SimPy model. And basically, the good news is that I know this seems convoluted, but the structure is always the same. And now what I'll show you is then if you want to add bits in, because obviously in reality your model is going to be a bit more complex than patient comes in, sees a nurse and leaves, but you just do the same thing and you just bolt stuff on. And actually it then becomes pretty easy to build up a model. So first thing you probably want to do is say, well, okay, there's probably more than one activity in my model. So imagine that our model is in fact patient arrives, they get registered at reception first, which needs a receptionist, then they see the nurse, and then they leave, okay? The good news is that is nowhere near twice as complex, okay? So all we have to do, if we want to add another activity that takes place after the last activity, we simply write it literally after that the previous one. So we just write the same thing again, but with a receptionist or whatever it may be, okay? We also have to, of course, add in, if that activity needs a new resource like receptionist, we have to add those bits in elsewhere as well. But fundamentally, that's all we're doing. We're just adding in the same thing of, okay, in that patient journey function, we're now adding in another with statement, and this one says with a receptionist, do this. Okay, and so if you look at SimPy example 2, now I've been quite friendly here, both to you and to myself. This is exactly the same as SimPy example 1, except with some new tweaks to it. And to note the new tweaks, I've put in hashtag new, so you can simply do Control and F, and search on double hashtag, and it'll automatically find all the new bits that have been added in. So to create this version of the model, before it was just patient arrives, nurse leaves. Now it's patient arrives, register at reception desk with the receptionist, then see the nurse, then leave. And I've only had to make 11 changes to do that. So in my G class, I'm going to need a mean time with the receptionist, because as well as the nurse. So I need to add that in. And I'm going to have it, on average, they spend 2 minutes at the reception desk. I'm also going to need, because I've got a new resource called receptionist, I need to specify how many receptionists I've got. So here I've specified 1. Then I've got my class that represents patients coming into the clinic. So in my patient class, I, as well as them recording how long they spent with the nurse, spent queuing for the nurse, I also need them to record how long they spent queuing for the receptionist. But again, it's just a replica of what I had below. Down here in my model class in the constructor, where I create my resources, where I created my nurse resource, I'm also going to create a receptionist resource in exactly the same way as I did before. I'm also going to add in 2 more columns to my data frame. So before I just have patient ID, queue time nurse, and time spent with nurse for each patient. But I'm also going to add in 2 extra columns here for the queue time for the reception and the time spent with the receptionist. Again, so you're adding in stuff, but it's just following the same format. Again, the attribute that's going to store the average queuing time with a nurse, I'm going to need one of those for the average queuing time with a receptionist too. Scroll all the way down, down, down. The generator, so all this was the arrival generator. That's all exactly the same. The new bit here is going to be, so in this case, I've added on an activity before the one I already had. So the activity we had before was this, where we started queuing for the nurse and we saw the nurse. That's all exactly the same as it was. But just before that, I've now added in an extra activity, and it's where they're going to start queuing for the receptionist. But it's exactly the same principle. So I set my stopwatch, say I've started queuing for the receptionist, I request a receptionist, I yield the request until that can be met, then I stop my stopwatch, I calculate how long I was queuing for the receptionist, I then sample how long I'm going to spend with the receptionist, I record these things in my data frame, and then I freeze in place with the receptionist. And you can see here, I highlight this, I'm freezing in place with the receptionist. Once I've finished, I then move to this piece of code here. I've now let the receptionist go, and I now start queuing for the nurse, just as and this is all the same code as before. Now, just a point of warning here, common mistake that people make when they're writing these things is to start from that indentation there. If you do that, the poor receptionist is going to be dragged along with the patient because you're doing all of this in the with block. So whilst you're in the with block, this says with the receptionist. And now in some cases, you do want that. For example, there may be a situation where you want to say grab a bed and then for the patient, and then that bed will follow the patient because the patient remains in that bed for this process as well. So in some cases you want to do that. But in most cases, this is people accidentally getting their indentation wrong and taking the poor receptionist with them. And anybody queuing up for the receptionist, just watching as the receptionist gets flung into the nurse consultation, that's effectively what you're doing. So be careful. You need to go, if you don't want the receptionist to follow you when you move to the next part of the journey, you need to make sure you come out of the with statement. But that's basically how it works. 11, oh sorry, there's a bit more. Let me go down to the next bit. So again, principle's the same down here where I calculate my run results. I do the same thing as I did with the nurse, but I just need it for the receptionist too. And then when for my trial data frame, I'm going to add in an extra column for the receptionist. And when I start up my when I've run a single run of my model. Sorry, my brain's melting now. When I've run a single run of my model, I'm going to store the results in the trial data frame, but that means I'm going to store both the receptionist and the nurse results, not just the nurse results now. Those 11 changes give you that extra step there. Okay, fine, I hear you say, but what if the system isn't linear? What if we've got branching paths? You want branching paths? You can have branching paths, and it's really easy to do. So again, well, before we come on to that, let me just explain a little bit about how this will work. And you saw a glimpse of this last week. So let's imagine we've got our system. Now patients arrive, they get registered at the reception desk, then they get seen by the nurse, and then 40% of them will just leave, but then 60% of them will then have a consultation with the doctor and then leave. Okay? So to deal with branching paths, we can just use conditional logic. We're in Python, so we can just use conditional logic. The way we tend to do this, if we've got a probability-based branching path, is to sample from a uniform distribution. So a uniform distribution is simply one where the probability of any value being picked is equal. Okay, so there's an equal likelihood of any value being picked. So if we sample from a uniform distribution between 0 and 1, that basically means pick me a value between 0 and 1 and any value is equally likely. And we can use this to determine how a patient goes down a particular branching path. And you saw a little bit of this in the exercise last week. What we do is we simply say sample from that uniform distribution, and if the value that you sample is less than the probability that we want to capture, then do it. In other words, if we say if it's less than 0.6, then this patient will have a doctor consultation. Why does that work? Easiest way to think about it, think about all the values between 0 and 1. 60% of them are below 0.6, below our probability, our threshold. So there's a 60% chance that a value in this range will be picked. That emulates 60% of patients going down that route. And that's as simple as that. That's why it works. So if we want to add in a branching path, again, if we look at SimPy example 3.py, again, I've just added in the new stuff over and above SimPy example 2. In this case, there were 12 changes that I made. So again, because I've got an extra activity in here now, I've got this doctor consultation. I'm going to need to store a average doctor consultation time, just as I did for the nurse and the receptionist, number of doctors. I've also got this one here because I've now got a path. I want to store in my G class the probability of moving down that path. I don't need to store the probability for both because there's only 2. So if they don't go down that path, they go down the other one. If I had 3 branches out or more, I'd need to store multiple ones. In my patient class, I'll also get the patient to store the time they spent queuing for the doctor. I've now got a third resource, being a doctor. I set up in exactly the same way as the other resources. I'm going to need to add some columns to my patient data frame. Sorry, my data frame that stores each patient against their queuing times and how long they spent. I now need the queuing time for the doctor and the time of doctor to be added. I also need to add a mean queuing time for this doctor, a mean queuing time for the doctor across all patients in this run. Then we get down to the meat of it. So in our model class, where we've got the patient journey, this is all the same as before. Patient comes in, sees receptionist, then sees nurse. But then we've got this new bit here where some of them, 60% of them, might then see the doctor. Okay. So again, exactly the same as before. It's just I'm just use a simple piece of conditional logic to determine if this patient is going to see the doctor or not. So I'll say if random.uniform, which 0 and 1, which will give me a random number between 0 and 1. If that's less than the probability threshold that I've said of 60%, in my G class, if that's less than that, then see the doctor. And I've written this in exactly the same way as all of the other activities for seeing the receptionist and seeing the nurse. Exactly the same format. Start your stopwatch, ask for the doctor, wait. Now stop your stopwatch, calculate the time. It's all exactly the same. Every single activity will follow this pattern. And this is what I'm trying to convey. I know it looks really complex at the moment, but it always follows the same pattern, which means if you need another activity, you just write another one of these things. So in this if statement here, 60% of them will, there's 60% chance that this will activate and they will then see the doctor as well. If that doesn't happen, if that patient isn't going to see the doctor, then nothing else happens. I haven't got an else statement. They'll just fall into the sink, basically. But of course, you could have an else. If you wanted them to go down a different path and do something else, then you could just put in an else statement here. In my calculate run results, I need to calculate the mean over the new doctor column as well. I need to capture the mean queuing time for the doctor over the trial, all the stuff I added in before, and I need to remember to add the mean queuing time for the doctor to my data frame for the trial as well. But again, it's the same thing I'm doing each time. I'm just adding in these bits. So once you've got the hang of doing this once, you can then theoretically build anything. You're just building it up out of these blocks. That's all you're doing. So it's like a cliff. But once you've scaled that cliff and you understand how SimPy is structured, it's really easy to then do these extra things. Okay, any additional questions that came as a result of that?
I think I have managed to get to all of those in the chat. But yeah, another one has just come in. How would you code in a line in the data frame for did this person see a doctor?
Oh, sorry, yeah, I meant to mention that. So you don't have to. So this is one of the reasons, other than pandas is beautiful and we all love pandas, of course. But this is another reason to use pandas. Because, of course, sorry, that's a really good, I'm really glad that came in because I completely forgot to mention that. So if I go back to the code, now, of course, we've now got a situation where not all patients will see the receptionist, all patients will see the nurse, but not all patients will see the doctor. Oh, where am I? There we go. Sorry, I'm not even seeing my own code. So only 60% of them will see the doctor. Some will just leave. Okay, that's all right. All that will happen is that entry will come in as not a number in pandas, and pandas will ignore it when it takes the mean. So if the patient didn't see the doctor, it's fine. It just won't be added in as a number. So pandas deals with that automatically for us. That's also really handy because when we stop the simulation at 120 minutes, some patients will be they've just come in and they're waiting to see the nurse. They haven't seen the waiting to see the receptionist. They haven't seen the receptionist yet. Or some patients will have seen the receptionist, but they haven't yet seen the nurse. So they will also have values that are incomplete. That's okay because pandas will ignore it. Okay, was there anything else?
No, I think we're good.
Okay, great, thank you. Right, so the first thing you all must immediately do is go and take a 10-minute break because that was a heck of a lot of information to take in. You are then going to work on this exercise. Apologies, we've got overrun by quite a significant amount of time. So I'm basically going to give you pretty much to the end of this session to do it, but we will come back very briefly at the end of today's session. This is the last thing you need to do anyway, but it is quite a big exercise that you're going to be working on in your groups. You're basically going to create this model in SimPy, where you've got patients coming into a GP surgery, they get registered at a registration desk, they then have a GP consultation, and about a quarter of them then also have to have a test booked in by the receptionist before they leave. The rest just leave. But also, in the same system, people are calling into the GP surgery on the telephone, and the receptionist the same receptionists are answering those telephone calls as well. And there's lots of details. I'm not going to read through all this. You can read through it. It does span over 2 slides, just to flag up. But there's lots of details here about how frequently they're coming in. Basically, what the surgery wants you to do is build a model to identify what's going wrong in this system. They've currently got 1 receptionist and they've got 2 GPs, and they're getting lengthy delays. So the first thing you should do is build a model of this system as it's described to you, okay? And all the details are here about what you need to do. Once you've done that, run the model, and see what's happening, and then try and fix it. So see, how do you think? And they're open to suggestions about anything, how you might go about improving the system, chucking in more resources, changing bits of the pathway. Be as creative as you like. Okay. So, but go and take a 10-minute break because that was a lot of information. Apologies, that took a lot longer to explain than I anticipated. And I realised that was an information overload. But I'm hoping, if nothing else, that you saw, whilst this looks quite complicated, and it is in a way, once you've got your head around it, it's really easy to then build anything. You just need to get through this initial bit. And the good news is the structure is always the same. So you can look at the code that I've provided you and you will follow exactly the same structure for this. Okay, right, I'll stop. I promise I now will stop talking before Sammy mutes me. So go and have a break, go and stretch your legs, and I'll open up the breakout rooms now. At 15:15, go into your breakout rooms and you'll have an hour and 15 to tackle this exercise. Sammy and I will be floating around and help each other. This is complex stuff, but help each other, and you will end today by creating your own discrete event simulation, which is quite exciting, I think. Okay, I will stop talking. Right. Hi everyone, welcome back. I just wanted to pull you back for a couple of things, just to round off the session, and Sammy's got the PSG points from this morning's exercise to announce. But I just wanted to say, hopefully you heard my voice in the breakout rooms. You're all doing really well. So I've managed to get around to quite a few of the groups. You're all doing really well at this. This is not easy to get your heads around, and there was nearly a 2-hour lecture where I took you through all of this. You're all doing exceptionally well, and from what I've observed, you're all mostly there. So we are offering to keep the call open for those who can stay on. Sammy and I are happy to float around for another half an hour. If you do want to and you can stay on, you are welcome to go back into your groups in a minute and finish off, because a lot of you are nearly at the stage, I think, where you've got the model built and then you can start playing around with it. And there is nothing like the sense of satisfaction of building your very first model, getting it working and using it, because although so in the next session, basically that we'll have in 2 weeks' time, I'll show you some extra little bells and whistles that you can do with SimPy, including, sort of turning things into log normal and modeling resource unavailability and all that stuff. But basically, from what I've shown you today, if you can do that, you can build a discrete event simulation model, and that's a massive achievement. Considering it was only a few weeks ago you were learning the basics of Python. And I know a lot of people every year get a lot of excitement out of building their very first simulation model, because then the doors are open to you. So the offer is there if people can stay on and want to stay on. You don't have to, obviously, but you are welcome to do that. Yeah, absolutely, really, really well done to everything I've seen. There's a lot to take in, particularly this afternoon. A lot of heavy code that is quite odd code that you've not kind of encountered before. But you're all doing exceptionally well. I have to say, a shout out to RJ McCall as well. I mean, I wandered into your group earlier. You were doing really well. You were actually starting to really get this, and you were breaking it down methodically and sort of breaking it down line by line, and we're really getting the concept. So really well done. To everyone here. So I'm just going to hand over briefly to Sammy, who's I completely forgot. Apologies after lunch to get her to award the PSG points for the design exercise this morning. So Sammy, I believe you got some winners.
Yes, so in joint bronze we've got Antic and Motorola. Silver I've got TIA, and gold we have Agnes. I also just wanted to give out a couple of 1 points to Zylog, Pokey, Denise, and Arm for creativity and puns. So well done, everyone.
Excellent, thank you, Sammy. Yeah, really well done. Really nice creativity. You've all worked exceptionally hard today. As I say, SimPy is not the easiest thing to get your head around, but it's so powerful, and being able to walk away from these sessions and be able to actually build your own discrete event simulation models is a massive thing. So I will stop there. I will stop the recording, but I will reopen the breakout room. So anybody that can stay on and wants to stay on, please do so. For the rest of you, as I say, don't forget it is a study week next week. Sammy, can you run it? Are you off as well on leave next week?
I am also off next week.
Yeah. Okay. So we're both on leave. If you get stuck, I mean, please use your peer support groups if you've got questions, etc. There are people floating around and help each other. But I'd absolutely recommend. I saw at least one group suggesting getting together as a group next week and going over stuff. That's a really good idea if you're able to do that and use that time just to go back over things. I think is really sensible. So, but for the rest of you, we'll see you in 2 weeks' time, where we'll finish off in the morning with the second SimPy session, and then finally you've got to the stage where you can stop listening to my voice for a while, and Sammy will take over for module 3, where she'll talk about geographic modelling in the afternoon, and for the next few weeks you'll have Sammy. So thank you to everyone today. As I say, if you want to stay on, we'll reopen the breakout rooms now. Otherwise, see you in 2 weeks.